Time for us to do some practice with problems involving linearization, which is another way of saying time for us to do some practice with applications of tangent lines. As always, when you're doing practice, it's important that you do as much practice on your own as you can and use these videos as a supplement. Try these problems out. The more you do, the better that you get. And if you are following along, make use of the pause button. Go to, you're like, aha, I think I see what to do. And then pause. Do it and see how far you can get. And pretty soon, you'll be flying through these beautiful vistas of calculus. All right, let's begin. The first problem, find the linearization of f of x, which is this symbol here. It means the fourth root of x. Now, if we were going to write this in a more calculus-friendly way, which of course we want to be calculus-friendly, we are doing calculus, and we're friendly. So we would write this as f of x is x to the 1/4 power. All right, so we want to find the linearization of x to the 1/4 at x equals 625. Now you might think 625, what a random number. But actually 625 is not a random number. It factors in a nice way. See, 625 is really 5 to the 4th power. So if you were to multiply 5 times 5 times 5 times 5, the result would be 625. So that's the first sentence. The second sentence uses this to estimate the fourth root of 610. So let's proceed. So we're after the linearization. Again, linearization is just a fancy way of saying tangent line. So here is what the linearization will be. It'll be the value of the function at the point we're interested in plus the derivative of the function at the point we're interested in times x minus a. So we'll call this the linearization. So in other words, the tangent line. All right, so what do we need to find? We need to find what is the value of the function at a, what's the value of the derivative at a. You might be saying, do we need to find a? Actually, it's given to us. It's right here. This is what a is. So this is our value for a. So, well, some of this isn't so bad, because remember, we have f of x is x to the 1/4. So if I plug in 5 to the 4th, what would that be? Well, that would be 5 to the 4th to the 1/4, also known as 5 to the 1, or just 5. F prime of x would be what? Well, 1/4, because the rule is bring the power down, so we bring the 1/4 down, x, and now you subtract 1. So 1/4 subtract 1 would give us negative 3/4. So, well, time to do a little bit of math here. Plug in 5 to the 4th. Well, let's think about this. You know, it might be helpful for us to think about how to write this. Now the negative, that's really 1/4, because the 1/4, that's the 4 downstairs, and then x to the 3/4 power, right? Now, how should we think of x to the 3/4? Because we got to plug this in, right? So this is like 1/4, and then we have 5 to the 4th to the 3/4. Well, actually, look, it works really nicely. A power to a power, what do? What's the rule? The rule is if you have a power to a power, you can simply multiply the two together. So this is 1/4 times 5 cubed. Now, if we wanted to, we could simplify, because 5 cubed is, as we all know, 125, and 4 times 125 is 500. We might simplify later, but for now, let's just take that as is. All right, so we've now found our pieces. So we can say what our linearization is. We just plug these pieces in. We take 5, and then we add to that 1/4 times 5 cubed. That's our f prime of a, times x minus 625, because that was our a. So there's the first piece that we were after. We were after the linearization. Now, the second piece says use this. Okay, so now we get to use it. So how do we use this? Well, the key is to understand what the linearization is doing. The linearization, or again, the tangent line, is mimicking the function nearby. So it's a good approximation nearby. And by nearby, we mean near A. 610, relatively speaking, is not terribly far off from 625. So we could say, you know, f of x, it's like our linearization. So we could say that the fourth root of 610, that's what happens when you plug 610 into the function, because the function says take the fourth root of what you plug in. So if you plug in 610, you get the fourth root of 610. That's going to behave like, now we plug 610 into our linearization. So this part here, this is our linearization. You might call it L of x. So that's going to be approximately 5 plus 1 over 4 times 5 cubed times 610 subtract 625. Well, now we can start to make progress. 610 subtract 625. We can compute that. That's not so bad. That would be a negative 15. And notice, really, 15, we can replace that by 3 times 5, because there's a 5 there. So I can cancel one of my 5s. All right, so where are we up to? Well, we have a 5, and now, what else do we have? Well, 4 times 5 squared. 5 squared is 25, and times 4 is 100. So that's 100, and then minus 3 on the top. So 5 minus 3 over 100. Well, we can actually convert this to decimal pretty easy. 100th is 0.01, so 300ths is 0.03. So it's like 5 subtract 0.03, or 4.97. And there you go. And that's the estimate based off of the linearization. See, the key is, we were saying, estimating the fourth root of 610. Well, computing this is hard because 610 is not a fourth root, but it's near a fourth root. So we can say, let's use the information about the point nearby, which is easy for us to get a handle on, in this case 625, and then follow the tangent line at that point to get an understanding of what this should be approximately. All right, so that's sort of the philosophy. I have a point that's hard for me to compute directly. There's a nearby point which is easy for me to compute. Let me use the nearby point to help me get an estimate for what the point I'm after should do. All right, good. Nice problem. Good times, good times. Well, let's try another problem. So, suppose our function, we have y is 5x cubed minus 4 e to the power 3x minus 6. And we're told that x is 2 plus or minus 0.05. So what that's saying is that x falls within a range. So we currently have that, if you think about this, we're saying x is roughly in between these two values. So 2 subtract 0.05, 2 plus 0.05. So that's what I mean when we say 2 plus or minus. It says there's an error. We don't know it exactly, but we know it falls into this little piece. Now, the question is, what can we say about y? Okay, so we want to say, all right, given how much I'm perturbing in x, what can I say about how much I'm going to perturb in y? So let's think about what linearization tells us. So one of the ways to think about linearization is to say the following. We can say our linearization tells us that we have our function at a plus f prime of a times x minus a. Now the x minus a part, this is sort of the important key to understand what's going on with this problem. This is how much we're perturbing x. And so if I want to understand what's happening to my output, I can say, well, look, this f of a, that's fixed. This f prime of a, that's fixed. And then this is the part that's being perturbed. All right, now, what's our steps here? Well, let's get our linearization. And here we go. Now, by the way, how do we know we should get our linearization? There's a clue. It says linearization. See, that's a pretty good clue. I like those kinds of clues, the ones that are sort of like, look at me, pick me. Wonderful clues. They're the best. All right, back to our problem. So our function here, we can think of our f of x is 5x cubed minus 4e to the power of 3x minus 6. And what is our f prime of x? Well, take the derivative, 15x squared minus, now 4 is a constant, and if you're taking the derivative of e to the power of 3x minus 6, use the chain rule, it'd be e to the 3x minus 6 times the derivative of the inside, which means that you're going to get a 3 coming down, so you're going to have a 12 e to the power of 3x minus 6. So there's my function and my derivative. Where's my a? My a is the 2. This is where I'm centering at. It's where I'm trying to understand the function at. I'm asking what's happening at 2 plus or minus a little bit. So 2 is where I care about the function. What's the behavior of the function at 2? So here we go. F of 2 is what? Well, that would be 5 times 2 cubed. So that would be 40, because 2 cubed is 8, minus 4e to the 6 minus 6, which is 0, e to the 0. So that's minus 4. All right, good. 40 minus 4, and we call that 36. All right, well, now f prime of 2. So what is f prime of 2? Again, plug in 2. 2 squared is 4. 4 times 15. Well, that's 60. All right, and then we're going to take 60, and of course we subtract 12, e to the 0 again. So 60 subtract 12, and that would be 48. All right, good. So now we have some sort of idea of what the value of the function is plus the value of the derivative, which is giving us our slope, how steep our function is at that point. Kind of a large number, 48. It's pretty steep. Well, things tend to blow up. X cubed gets pretty quick in the long run. All right, well, what's next? Okay, so the next thing we need to do is think about our function here, our linearization. So we put it all together. So our linearization says we have 36 plus 48 times x minus 2. Now, here's the idea. If I want to get an estimate for the corresponding range for y, what I'm going to do is I'm going to get an estimate for the corresponding range of the linearization. How does that work? Well, think about sort of the picture. So let's just sort of sketch a picture of what's happening here. So you have a function. Here's our function. And we have our linearization, our tangent line. So here's our linearization. Now, at our point A, which is our tangency, we're going to go in between, plus or minus a little bit. So this is our A minus a little bit to A plus a little bit. And our goal is to say what's happening to our output. So we're interested in the output of the function, which should be this little piece. This is the output of function. So in other words, between the 2 plus or minus, the A plus or minus a little bit. But what do we see? Well, that can be hard to compute because then we'd have to see well, now we've got to compute things like 2.05 cubed and e to the 0.15, and these are tricky. But we say, hey, check this out. I can, lo and behold, look at this piece, which is the output, not of the function, but of the linearization. And what do you see? The output of the linearization, it's not perfect. It's not exactly the output of the function. And that's not surprising because linearization is about approximation. However, when we are nearby, the output of the linearization is a reasonable estimate for the output of the function. So we can say, okay, so if I can get an idea for what the output of the linearization is, that's the way I can get an estimate for the corresponding range for y. And notice it does say here, we're after an estimate, not after an exact value. So we're not going to exactly nail our range for y, so we're not trying to be like, this is exactly where y can go between, we're just after an estimate. So let's get back to our story here. Our story here is how much can I vary from 2? See, if x is 2 plus or minus 0.05, another way to think about that is that I could also phrase that as x minus 2 is off by 0.05. So I really say, look, this is like plus or minus 0.05. Okay, well, scale 48 times 0.05. Well, 48 times 0.05, that sounds hard, but think of it this way. What's 48 times 5? 40 times 5 is 200. 8 times 5 is 40, so it would be 240. Now to get to 0.05 means you have to move the decimal over, so So it would be 2.4. So what do we get? The corresponding range for the linearization is 36 plus or minus 2.4. So this is an estimate for what's going to happen for y. So if we know that x is 2 off by 0.05, then we can say, well, y should be 36 off by about maybe up to 2.4. Now, again, you might say, well, is it guaranteed that y is going to stay in this range? It could pop out. And it could be the case that the range misses a little bit of what the real output is. But it's an estimate. So that's good enough. So this is an estimate for the range of y. And there you go. Nice. Aha. Good. Good. All right. That was a fun problem. So, well, let's do another fun problem. Well, a word problem. These are always fun. You have recently been hired as the chief architect for one of the pyramids being constructed by Pharaoh Sneferu in Egypt. After some consultation, the Pharaoh has agreed to a pyramid design that is 500 cubits. And by the way, a cubit here is not a misprint. A cubit, that's a measurement of distance that was used in ancient Egypt. All right, so it's 500 cubits wide and 300 cubits high. The volume of a pyramid is 1/3 b squared h, where b is the length of one side of the base and h is the height. So that the pyramid will require 25 million cubic cubits of stone. Oh, that's kind of a fun thing to say, cubic cubits. Aha. Now, after getting in touch with your stone contractor, after all, we all have our favorite stone contractor, you discover that there are only 23 million cubic cubits of stone available. The Pharaoh gives the go-ahead to build a slightly smaller pyramid, but with the same proportions as before. Use linearization to estimate how many cubits smaller the base of the pyramid will end up being. So, what's the idea? So, initially, the Pharaoh wanted the following. So, we have a pyramid. Now, if you're not familiar with a pyramid, it has 4 sides and goes up to a peak on the top. Okay. Well, I should say there's a couple different types of pyramids. This is the ones that you found in ancient Egypt. All right. So, there's this nice ratio, right? So what's happening is that you have 500 cubits here on the bottom, and then the top is from the base down up to the top would be 300 cubits. Now, there's not enough material. We're short. So if we're short, what's going to happen is we have to make changes. And so the changes here are going to be, it's a smaller pyramid, but it's like you hit reduce on like a photocopy machine. So other than the size, the proportions are the same. So similar proportions, different size. So our goal here is to say, well, what's happening? In particular, we want to get an estimate for what's the size of the base. So, we're laying our foundation. We need to know how big our base is. Now, how are we going to go about this? Well, what do we need? We need to think about what we've been told. So let's think about what we have here. So we have a volume for a pyramid, and they gave us a formula. Whenever they're giving us a formula, we're probably going to say, that's probably a useful thing to know. So we're going to keep track of that thing. So volume is 1/3 b squared h. Okay, so now we have a formula for volume. And we know something else. We've lost some volume, right? Because the original design was going to be 25 million. The new design is 23 million. So our change in our volume, how much volume we've modified, is minus 2 million. So that's a lot of cubits of stone that we've just lost in our volume. Well, what can we do? Well, what we can do is we can use the idea of saying, well, we want to see how much our inputs change as our outputs change. Now, right now, there's kind of a little bit of a glitch. The volume, notice, depends on both the base and the height. So, what's our glitch? That's two different numbers. That sounds like a function with two inputs. That's multivariable. We're single variable. So we need to get our function rewritten as just a single nice function. Okay, so how do we do that? Well, here's the idea. So what we can do is there's one other key phrase here, and we've already talked about it, but I'm going to highlight it. The same proportions. Well, what does that mean? Well, that means that we're going to scale everything. And so whatever we scale the base by, we're going to scale the height by. So that says in particular, if I think of the ratios of base and height, they're not going to change. So if we take that into account, we can say that our base to our height in our original design is 500 to 300. So I can rearrange this and I can say, hey, let's move the h across. Notice we can cancel a bunch of zeros. So we could say whatever our height is, it's got to be 3/5 of our base. So now we can update our function and say our volume function, if I replace the height by 3/5 the base, the 3/5 times a third becomes 1/5. And then we have a b cubed because we have b squared originally and then the b because of how we replaced h. All right, well, we're making good progress here. Not there yet. What else do we need now? Well, what are we after? We're after a change in b. And of course, the question you are probably still wondering, what does this have to do with linearization? How is linearization coming into play? So here's the idea. One of the ways that linearization can be thought of says that a change, all right, in terms of functions y and x, change in y is approximately our derivative at a point we know times change in x. Now, of course, the variables y and x, there's nothing sacred about that. So what can we say? Well, we can say, for instance, instead of having y, we could have that be v. It's approximately the derivative of our function evaluated at some interesting point times our change in our input. In our case, b. Our base is our input. So, well, our derivative, okay, so here, if we think of this as our function, or it's a function of b, and that's just perfectly fine to have b be a variable. So 1/5 b cubed. The derivative would be what? Well, 3/5 b squared. Now, where do we plug it in? That's the question. And what I do is I plug it in at the point where I already had information. So we know about the 500. See, that's the place where we're trying to understand what's happening. So we can say the following. let's put it all together and see what pops out. So the change in volume is minus 2 million. That's approximately what happens when you take 3/5 times 500 squared, because that's the original design had B equals 500, times the change in your base. Now, this looks intimidating, but we're not going to be intimidated. We're going to say, hey, look, there's a 5 here, and there's 2 5s there, so that's good. I can cancel one of the 5s, and I have a 1 and a 5 coming from there, 15. And then I'm going to have 4 zeros, because every 0 here gets made doubled, right, because of the square. So times change in our base. All right, so here's where we're at. Now, we put it all together. And we say, let's start canceling. Now, what we can do is when you have bunches of zeros, you can cancel zeros by saying, really, you're dividing by 10. So we can cancel a whole lot of zeros really easily. So we get to minus 200 is 15 times our change in our base. So move the 15 across, and we get that our change in our base is equal to minus 200 over 15. But of course, 200 is divisible by 5. So if you divide out by a 5, you'll get a minus 40/3. And what are the units? Well, the units are cubits. So that is how much the base will change. And notice, we wanted to get an estimate. So this is really, there is an estimate here, because this is, see that approximation of how many cubits smaller. So how much did we change? So we're going to have to change by negative 40/3, almost 13 or so cubits. Well, it was 500 cubits to begin with. Losing 13 isn't so bad. All right, now, on a side note, the name Sneferu is a real name of a pharaoh. And he did build a pyramid. And he did not really do a good job with his stone contractor. So you can go look this up. This is history. It's like, hey, I'm here to learn math, not learn history. So you can look up, there's something called the bent pyramid. And if you look it up, you'll see a picture. And you can see that from the side, it looks something like this, where originally it was going up at one angle, but it seems like about halfway up they said, oops, don't have enough stone, so they had to make it shallower. So, well, that's what happens when you don't have a good relationship with your stone contractor. Or maybe we should say that's what happens when you don't do a good job of planning ahead. Well, as the saying goes, measure twice, cut once, right? Okay, well, that's a good problem, fun problem. All right, let's do one more problem. So we have g of x is a function, 3 plus e to the power 1 minus x minus 2x, and h of x is x times g inverse of 2x minus 4. So our goal, use linearization at x equals 3 for h of x to estimate h of 3.1. Now, in some sense, trying to compute the function at 3.1 would be really hard, because what would we have to do? In order to compute the function at 3.1, we'd somehow have to find the inverse of this function. And it's not even clear to begin with this invertible, but it is. There's a good story that we can tell later on that shows that this is indeed an invertible function. But we would never be able to find the inverse, so we could never plug it in 3.1. Now, of course, a computer can find a really great numerical approximation, but they're doing a computation, so they're doing something similar to what we're going to do. So, okay, so how can we proceed? Well, we know how to proceed. It tells us. It says linearization. So we know the idea, the philosophy here. We're going to find a tangent line, and then we're going to say, hey, instead of trying to find the function at 3.1, which is the exact value, we'll find what's happening to the tangent line at 3.1, and that's our approximate value. That's our estimate. All right, so we have a plan. All right, So we need to do a couple of things. So in particular, well, we need to do our linearizations at 3. So our linearization, I'll call it L of x for linearization. That would be our h at 3, where we're taking our tangent line at, plus h prime of 3 times x minus 3. So we need to get these numbers, h of 3 and h prime of 3. Well, so let's begin. Let's start with h of 3. So that would be equal to 3 times the inverse of 2 times 3 minus 4. Okay, so that's 3 times the inverse of 2, right? Because you plug in, you get 6 minus 4 is 2. So now we need to find g inverse of 2. Well, this should be fun. So let's think of g. So what do we need? We have our function 3 plus e to the 1 minus x minus 2x, and we want that to be equal to 2 because we want our function g of x equals 2. Figuring out for which x is that holds, for which that x that's true, that's what it means to find the inverse of 2. All right, so we start going, what's possible value for x could this be? Now, we should be suspicious that when we're trying to find the inverse of functions at points, it doesn't mean try to find the inverse of function everywhere and then plug in, because that's a lot of work, and sometimes it's an impossible task. Instead, we should say, I wonder if they gave us a nice point to work with, because my math teacher likes me. Well, of course we like you. You're a great person. What's not to like? So, is there a nice value for x? And I will say there's a built-in clue here. And that built-in clue is upstairs. Do you see this e to something? See, e to something is generally not a very nice number, except when it's e to the 0. E to the 0 is lovely. Which value of x would give us e to the 0? X equals 1. And by the way, 1 is also a great number. So what do we get? Well, we get 3 plus 1, which is 4, minus 2 times 1, which is 2, and it works. Aha! So we see, lo and behold, x equals 1 works. So that tells us that g inverse of 2 is 1, which tells us that h of 3 is really 3. Good to know. Now, we're not done. We now need to find h prime of 3. Okay, so switching gears. To find h prime of 3, we start with h prime of x. So here we're going to do a product rule. So the derivative of the first times the second, and then we're going to add to that the first times the derivative of the second. And so we need to take the derivative of the inverse. Well, we've done that before. You should have done it before. I hope you're doing all of your practice here. So remember how to take the derivative of the inverse. It's 1 over the derivative of the original function at what happens when you plug it into the inverse. Now, there is a chain rule coming here, so don't forget there's still 2x minus 4 on the inside. So there's one last piece to finish it up. We need to multiply by the derivative of 2x minus 4 on the outside. So times it by 2. So there we go. Now, next step is plug in 3. So here we go. H prime at 3. Well, that's g inverse of 2, because that'll be 6 minus 4 is 2, plus, here we have 3 times 2, which is 6, times 1 over g prime of g inverse of 2. But we know what g inverse of 2 is because we computed that. See, g inverse of 2 is 1. So we say, aha, this is really 1 plus 6 over g prime of 1. So what do I need? Well, the next thing I need is, what's g prime of 1? Well, let's come to the side, do some work. G prime of x is, the derivative of 3 is 0. Derivative of e to the 1 minus x is minus e to the 1 minus x. And that minus is coming from the chain rule. So the derivative of e to something is e to that something, then times the derivative of the inside. And the derivative of 1 minus x is minus 1. So that minus is coming from the chain rule. the derivative of minus 2x is minus 2. So g prime of 1 would be minus 1 minus 2, which is minus 3. So, all right, that's fine. So what do we have? We have 1 plus 6 over negative 3. Or, that's really 1 minus 2, which is negative 1. All right, well, hey, that's very convenient. Okay, so we're ready to say what our linearization is. So at this point, we now say our linearization is L of x is going to be 3 plus the derivative, negative 1, times x minus 3. So we can say our h of 3.1 is approximately what happens to our linearization at 3.1, which is 3 minus 3.1 minus 3. Well, if you look, you can actually see something that's kind of happening here. So, see 0.1, 3.1 minus 3, this will give us 0.1. 3 minus 0.1 is 2.9. All right, so there you go. There's our approximation for what happens to our function h at 3.1. So even though we can't get a handle on it directly by saying, hey, at least I can understand what's happening at 3, 3.1 is close to 3, and so I can get an estimate for what it should be. All right, so the theme for today, tangent lines are good estimators. So if we're trying to understand what the behavior of the function is, well, we can try to understand what's the behavior of a nearby tangent line, and that should give us a pretty good idea of what's going on. Not perfect. It's an estimate, but pretty good. All right, thanks for coming.